Okay, a follow-up day on 6.5. At the top of the screen there is a super important definition, guys. You're going to see this a lot. It's the definition to find the average value of a function. It came from the mean value theorem of integrals. I put some stars above there. You want to know the average value of a function is 1 over b minus a times the integral from a to b of f of x dx. And our learning target, plain and simply, is that I can determine the average value of a function. So let's take a look at number 2 real quickly and realize we have a parabola. A parabola that would have its vertex at the origin, and it's obviously going to be opening upwards. And it's going to open up just like so. So the bottom point, I think we'd all agree, would be 0, 0. Way up on top, the highest point that we'd see would be 3, 9. So all the y values between 0 and 9 are going to be achieved. There are, definite points that relate to that. There are infinitely many points, guys, on this curve. So the big question is, what's the average y value? Now, it's probably very tempting to take your 9 and your 0 and say 9 plus 0 is 9, divide by 2, and you get 4.5. Well, we've just seen from the setup of the mean value theorem for integrals, though, that honestly, if you wanted to find the average value of this function, you would take 1 over b minus a, 1 over 3 minus 0, integrate between 0 and 3 of x squared dx. And guys, that is going to tell us what the average y value is on this interval. So, obviously, 1 over 3 minus 0 is just 1/3. What's the antiderivative of x squared? What would we get here? X cubed all over 3, and then we can, say we're going to plug in a 3 and a 0. Now, if you'd like to actually just pull out the 1/3 and the 1/3 and make it 1/9, you could do that. There's nothing wrong with that. And from here, you could see that you'd plug in 3 cubed minus 0 cubed. And 3 cubed is 27. And real quickly, you'd realize that it's 1/9 of 27 minus 0. 27 minus 0 is 27. If you take 1/9 of that, you get 3. That's the average value of y on this interval. Okay? You might notice that what's happening is we do have, as x is relatively smaller, our curve remains closer to that x-axis for those x values as we start off. So this is a nice way to actually find the average value of a function. We're going to do that a lot. The second part of the lesson today, here's our next learning target. I can use the trapezoidal rule to estimate integrals. Now, the trapezoidal rule in many textbooks are actually, you will have this linked right to LRAM, RRAM, and MRAM. Our book actually doesn't keep it there, and that's fine. We get to review a little bit. But first of all, a little bit of geometry review. You can know that the area of a trapezoid is 1/2 base 1 plus base 2 times the height. And the height, in all truth, is really the distance between the bases. Also, very, very importantly, the trapezoidal rule could be thought of as simply the average of LRAM and RRAM. Take your LRAM estimate, add it to your RRAM estimate, and divide by 2. And that's actually what the trapezoidal rule is. But a couple of things I'd like to point out. The trapezoidal rule is a wonderful approximation tool. We're going to talk about why this formula is going to work out and then we're actually going to go through and try to work out an estimate. But suffice it to say, I hope as you're looking at this picture here, you're going to hopefully quickly note that if I draw in a trapezoid, it's very different than drawing in a rectangle. You don't have quite as much of a portion of a rectangle coming over the curve or being inscribed underneath. So you're getting closer to the real curve itself as you're looking through this. I guess what I really want to talk to you about is that the bases are going to be vertical. These are trapezoids that are turned on their sides. They look something like this. So our bases are actually going to be measured by y values. The distance between the bases, which we will call our heights, would be our delta x. Delta x was always the base of a rectangle. For this problem, delta x is always the height of a trapezoid. Okay, so that's the first thing that we need to be aware of. And as you're looking at this little picture right here, you might be thinking, okay, well, I definitely see all these trapezoids coming into play. And then they give you this very obscure looking formula, and just the complexity of it undoubtedly is going to be intimidating for some students. You know, sometimes kids look at that and they're like, oh my word, that looks super complicated. You've got a b minus a over 2n. Inside those brackets, undoubtedly the first thing kids notice is, hey, a whole bunch of those f of x values have a 2 in front. Some of them don't have a 2 though. And that can beg the question, why is that? And I guess what I want to point out to you is your first f of x value and your last f of x value are the ones that don't have a 2 in front. Everything else does. But let's see if we could actually go through a proof and talk about why this works.